Hi everyone, in this module we'll look at waves starting with 2.1, types of wave motion. So the first question is, what is a wave? Well, a wave is an organized disturbance that's traveling at a well-defined wave speed. It's a propagation of energy. So some examples of waves are sound, light, water waves, a wave on a string, and there are a couple of different ways to classify waves. One way is by whether or not the wave travels through a medium or whether it requires a medium. So mechanical waves are waves that require a medium, which means a substance, to propagate. So whether that's air or a solid, there needs to be some type of medium. Electromagnetic waves, on the other hand, are created by oscillating electric and magnetic fields, and they do not require a medium to propagate. So they can travel through a vacuum. And this is important because that's how we get energy from the sun. So in this section, we're going to focus on mechanical waves. A mechanical wave is started by a disturbance. So this could be a single wave pulse, or it could be a periodic wave source, which creates continuous waves. So an example of this is for a wave on the string, maybe moving the end of the string up and down, or for a ripple in the water, just a disturbance on the top of the surface of the water. That could be the wave source. So let's look further into mechanical waves. Mechanical waves can further be classified by the direction of the motion of particles in the medium with respect to the direction of propagation of the wave. So the first category is transverse waves. In transverse waves, the particles in the medium move perpendicular to the direction of wave propagation. So an example here is a wave on the string. If you were to move the end of the string up and down, it would send a wave in that perpendicular direction along the string. So each particle in the medium only moves in this vertical direction, but the wave is sent in that horizontal direction. Another example of this is at a sports arena. When everyone does the wave like this, everyone individually moves up and down, but then the wave appears to go around the arena, which is in that other perpendicular direction. Okay, so longitudinal waves, on the other hand, are waves where the motion of particles in the medium is parallel to the direction of wave propagation. And sound is a good example of longitudinal waves since they're vibrational waves. And another example of this is a slinky. If you were to hold the end of the slinky and then just push it in that horizontal direction, it would also send a wave in that horizontal direction. What would happen is the components of the slinky would compress and expand, and that's how the wave would travel through the medium. So those are vibrational waves, and we'll look in more detail on longitudinal waves in our section on sound. So there is a third type, which is surface waves, that have both components of transverse and longitudinal waves. And ocean waves that you see are surface waves. So actually the particles in the medium are moving in a circular shape like this, and overall it appears like a wave, and it creates this propagation of energy. So all three of these waves are a propagation of energy throughout the medium. There's no overall macroscopic motion of the medium as a wave passes through it. So we'll now focus on transverse sinusoidal waves. The reason is that these are important waves because the source of the wave can be an object in simple harmonic motion, and any periodic wave can be written as a sum of transverse sinusoidal waves. So there are a few important properties that are used when describing a wave. I've sketched a wave here in y versus x. So this is its spatial component here. First of all, crest and trough. The crest refers to the peak of the wave, so the highest point above equilibrium that the particles in the medium reach. Then the lowest point is the trough, so that's this lower kind of the dip here. And then we also have amplitude, which is the same as we used it in simple harmonic motion. So it's the maximum displacement of particles in the medium from equilibrium. So that can be drawn either above or below equilibrium. Both of those quantities are the amplitude. And that's a unit of length, so generally measured in meters. Then we have wavelength. The wavelength is the length of one complete cycle of the wave. We can draw that anywhere that encompasses one complete cycle. So I've drawn it starting from 0 here, Also, another easy way to see this is from crest to crest or trough to trough. So the red line shows the wavelength from crest to crest. And again, that's a unit of length in meters. Another common unit is nanometers, so any unit of length there, but the SI base unit is meters. Okay, I have just a few more definitions to go over. So period and frequency will also be used when describing waves. So we've seen these definitions before. Now the period, which is capital T, refers to the time for one cycle of a wave. So the time for one cycle of a wave to pass a point in the medium. And generally that's measured in seconds. This could also be thought of as the amount of time per cycle. Okay, so frequency, F, is the number of cycles per unit time. So it is the inverse of the period, and that's measured again in hertz, which is 1 second inverse, or 1 per second. Then we have wave speed. This is a new quantity that is very important for these waves, which will travel at a constant speed in a medium. Our equation for constant speed is distance over time, and we know that in one period, the waves travel one wavelength. So we can plug in lambda over t here, and then t equals 1 over f. So usually this equation is written as v equals lambda f, and this gives the wave speed for any wave. So we have lambda, wavelength in meters, and then frequency in hertz, and we get the wave speed in meters per second.
Example 1, a fisherman notices that his boat is moving up and down periodically due to waves on the surface of the water. It takes 2.5 seconds for the boat to travel from its highest point to its lowest point, a distance of 0.53 meters. The fisherman sees that the wave crests are spaced 4.8 meters apart. What is the wave speed, frequency, and amplitude? Okay, so we're given the distance between two adjacent peaks, which is the wavelength, 4.8 meters, so we already have that. And then this distance from the peak to the trough, or the crest to the trough, will be twice the amplitude. So we can find the amplitude by taking 0.53 meters divided by 2, which gives 0.265 meters. Okay, then we also know that it takes 2.5 seconds for the boat to travel from its highest point to its lowest point. It has to go back up to its highest point for that to be one full cycle. So we're looking at half a cycle here. So our period will be twice that time, 2.5 seconds times 2, which is 5 seconds. And the frequency is 1 over that since they're inversely related, so 0.20 hertz. And then lastly, we can find the wave speed, v equals lambda f. So 4.8 meters times 0.2 hertz, which gives 0.96 meters per second.